Hello everyone. Today I am here to discuss with you an important topic, thermal stresses, or you can say temperature stresses under this subject, strength of material. So let's introduce myself. Myself is Dr. Ishad Ahmad Khan, working as Associate Professor in Department of Mechanical Engineering, Sagar Institute of Research and Technology. Let's come to the topic, thermal or temperature stresses. So the thermal stresses are stresses induced in the body due to change in temperature simply. Thermal stresses are set up in the body when the temperature of the body is raised or that temperature is lower down. The body is restricted by some external mean to stop it to either of expanding or contracting. Let's discuss in detail. Suppose we have a body having length L and diameter D. If suppose temperature is raised by delta T degree centigrade, and one more thing, the both end of this body are restricted. So free thermal expansion in the bar, we can use the simple formula alpha delta L, where alpha is a coefficient of linear expansion, or you can say linear thermal expansion. So this is free thermal expansion. If it is a free, both it is not restricted here. So by this amount, if you find out by this amount, if you put the value of alpha and delta and multiply by L, so definitely it is expand by this length. So calculate now, get the thermal strain. So as we know that strain, we can know change in length upon original length of the body. So change in length, how much here? It is equal to the expansion. So expansion alpha delta L upon original length is L. L is cancel out. So it's become alpha delta. This is this by this relation we can calculate thermal strain, and if by multiply by the Young modulus of the material, we can get the thermal stress. And as we know that the shape of that body is circular, so we can say the area of cross section of bar pi by 4 d square. So if we know that the cross sectional area, we know the thermal stresses. If we multiply with the cross sectional area to the thermal stress, we can calculate the compressive force developed in the bar. Simple, you just multiply this term with this. So compressive force set up in that bar, we can calculate if it is for if any single bar which is made of or one materials. So we can use simple these relation to calculate stress, strain, and compressive force developed in the bar. If it is restricted in the both, if it is not restricted, so it not state won't be developed, state will not be developed, and you can't be. So if stress is not developed, so it is not possible to calculate the compressive force inside developed in the bar. So one thing you have to remember, there must be restriction at the both side of the body. So let's talk about the thermal stresses in the composite bar. So let's discuss here. See this diagram. This is a composite. This is a composite bar, we can say, which is made of the copper and copper. Copper is in inner part, and the outer part is made of steel. Means there is a composite of two material which are which are set up is like this. You can see in the diagram. So one thing you already know, the coefficient of thermal expansion of copper is more than the steel. So if the both steel and copper are free, so if the temperature is raised by delta degree centigrade, so Here, this copper one expand till this length. You can see here up to this length, copper. And because the coefficient thermal expansion of steel is less than the copper, so it will, if it is a free, so it's reach somewhere here in this position. You can see because they are in composite one, so copper having the more coefficient thermal expansion, so it's try to drag this this steel to a new position which is ahead of its previous position if it is a free. So you can say with this action, this steel feels some tensile stress. Okay, and then when the copper free, so it will come up to this position. You can see red line what I am drawing, but because of coefficient thermal expansion of the steel is less, so they are settled down themselves at the final position is this one. So hope you are understood. If free, copper reach here. If steel free, it can reach this position, this one, this position. But both having the different coefficient thermal expansion, they are settled down at somewhere somewhere mid positions or some different positions. So we can say here conclude that because the copper having the more coefficient thermal expansion, so it's come under the compression and steel has less, so it's in tension. So let's drive a relation for the thermal stresses. So first, okay, let's erase this part. Okay, and so okay, next slide. So let's assume sigma C stresses in copper rod and sigma S stresses in the steel one, and AC cross-sectional area of copper rod, and this is AS cross-sectional area of steel. For equilibrium condition, tensile force in steel rod equal to compressive force in copper. So as I told you, they are settled at somewhere midpoint. So which having more coefficient thermal expansion, they come under the compression, and which having less the coefficient thermal expansion, they come in tensile. So tensile force set up in steel and compressive force set up in that copper rod, so it would be the equal. And let's assume two parameters alone. Again, then alpha is a coefficient of thermal expansion in steel and its coefficient thermal expansion in the copper. Now, we can say the elongation in steel equal to elongation in the copper. And this elongation can be represented by the due to elongation due to temperature plus due to the tensile force. Because the copper drag or pulling ahead to the steel. So elongation of copper due to the temperature and minus due to the compressive stress offered by steel on the copper. So temperature strain plus tensile strain in steel equal to temperature strain minus compressive strain in the steel. So this statement we can write mathematically. The temperature strain alpha del T, and this is for steel. That's why there is a suffix S. Okay. Similarly, tensile stress. So we know the tensile is strain is stress upon the Young modulus. And for the copper one, alpha C del T minus del C upon EC, then this rearrange this relation. So it's a become this this term here come here. So we can write like this. So sigma s upon ES plus sigma CE is equal to alpha C minus alpha S del T. And this is called also called as a strain. So this strain you can also write in term of stress or in term of strain. So whatever question will come to calculate the numerical, we can use this relation to calculate the stress or strain or anything which may be asked in that questions. So hope you are understood the concept of temperature, stress in simple bar as well as in composite bar. Thank you so much for attending this lecture.